So here we are at virtual lecture number 11, and again continuing with the transition metal stuff and building upon what we had in the last lecture. That was mentioned that many transition metal complexes and things like that are colored. The question is, why is that? Well, they're absorbing energy. That's the answer, the short answer anyway. And then you see the complementary color to which they absorb. And so we'll look at this in a little more detail as well. And so this again all depends upon the spectrochemical series. Okay? So let's look at a practical example of this. Let's use iron again. And let's use iron 2 once again. And we have 3 complexes. One that has 6 cyanides, one that has 6 waters, and one that has 6 chlorines. Okay. And then let's say, and again, it's impossible to actually know what color something's going to be unless you take its spectrum. But let's say one of these is red. One is green. And one is blue. Which one's which? That's the question again you might be faced with on an upcoming homework or on the third exam or the final exam. And again, it may seem like this is one of those weird math problems where Jane's in a car driving past Jack, who's standing on a curb going 60 miles an hour. With the Doppler effect, she says, hello, what are their ages? But it's actually very straightforward. You just have to be able to think in a logical process to do this. All right, so I'll write my colors down over here so I don't forget. Some space to work. How do you go about this? Again, this all has to deal with the spectrochemical series. So the first thing we've got to be able to do is ascertain which one of these has the largest delta O, which one has the smallest, and then of course the third one will fall in between them somewhere. Okay? So if we flash back to the spectrochemical series for a second, there's halogens, then oxygen donors, nitrogen donors, phosphines or phosphorus donors, cyanide, and carbonyl. All right, over here on this side, we're going to have a small delta O. Delta O will get bigger as we move from left to right. So cyanide and carbonyl and phosphines are the ones that have the biggest delta O's. So, based upon this, let's rank these. And let's do it like so. The smallest delta O, the largest delta O, and one in between, medium, intermediate. Call it what you like, it doesn't matter. Which one of these then has the smallest delta O? Well, if we look at our complexes, that's going to be large. This is smaller, but because we have 6 chlorines, that's the one. So I'll just put the ligand down since the iron metal is the same. What about the largest delta O? Well, do we have a phosphine? Do we have a carbonyl? No, but we have cyanide. And that is the largest one. So by process of elimination, or you can go through by the same arguments, the water complex is in the middle. So that's the first part. Now we can assign the colors. But guess what? We can't just pick among these and figure out which is which yet. Because you or I as you see the complementary color to the one absorbed. So what the heck does that mean? Well, on the handout for this lecture, you'll find this here picture. The color wheel, which you probably saw back in elementary school, middle school, something like that maybe. Right? What I mean by this is if a complex is absorbing violet, you go across through the middle, where do you end up? Yellow. Yellow is the color you see. So each of the colors there have a complementary color. If you're seeing that color, this complex is actually absorbing the complementary color. Okay? So, what then do we also have to do? Let's cut the board in half for a second. You have to understand what the energy relationships are between the colors. And so this goes back to that old equation, E equals H nu. This is frequency. And you can also substitute in and rearrange that E is hc over lambda. H is Planck's constant, c is the speed of light, lambda is wavelength, and that's the important thing for us. And so you don't actually have to worry about doing any calculations. We're not going to bother with that either. The important thing to remember is energy is equal to 1 over wavelength. Okay? And so in order for a complex to absorb, what it must do is absorb energy to promote an electron. And so, and this can happen with any electron configuration. If we take a D2 configuration, a simple one, but it could be 6, it could be whatever, except for D10 or D0, because there are no electrons, more on that later. It absorbs some light, and then you promote the electron up. When it does that, that's what produces the color. And so can you see the color or not? That all depends on what the complex itself is. But normally, yeah, you can with these things. And so this energy, or this wavelength, is equal to the energy, which is delta O. Delta O is proportional to the absorbance energy, which is 1 over wavelength. And so again, in order to do this, you have to understand the relationships between the wavelength and the energy. So if you look again on your color wheel here, red is between 800 and 650. Orange is between 650 and 600. If you go all the way around, violet is between 400 and 430. So here's another, I guess, thing you have to memorize, but it's straightforward. Long wavelength. Low energy. So something that absorbs red light, that is low energy absorption. Conversely, we can not call that high. How about short? A short wavelength is a high energy absorbance or absorption. So, what would be the highest visible one? Well, that would be violet. And what about the lowest? Something that absorbs in the red. If the wavelength is longer than, say, 800 nanometers, what is it doing? It's actually absorbing in the next region of the visible spectrum, the infrared. If its wavelength is shorter than 400, what it's doing is it's absorbing in also the next region of the electromagnetic spectrum on the other side, and that's ultraviolet. And so one of the things that you may realize, just based upon that, is why we put sunscreen on when we go outside, right? One of the problems that can cause sunburns and things like this isn't really so much the visible light from the sun, it's the ultraviolet. So you get these skin creams with UV protection. That's high energy waves with short wavelengths. And so this all fits in with that too, if you like. What do you do to heat something up? We use infrared. So anyways, this is the important thing is the size of delta O is equal to the absorbance energy, which is inversely proportional to the wavelength. And as a result, a long wavelength, something that absorbs in a long wavelength, that being like red or orange, it's a low energy absorption. If it absorbs in a short wavelength, violet or blue, or something like that, it has a high energy. And if you look at this and see the relationships between the wavelengths, then you can answer this question. We have three things here, not two, but it still will follow biological evaluation. And don't worry, the color wheel will be on the exam and the final exam, so you don't got to memorize that. It'll be the exact same one that's on your handout for this virtual lecture. Okay, so let's get back to business. We have our color list here, red, green, blue, but that's not what it absorbs, that's what you see. So we have to figure out what does it absorb. So let's start with this one. You see red. You see a red complex. Or this lecture is so terrible, it makes you see red because you're angry. I don't blame you. Anyway, trying to be funny, probably not being. All right, we have a red complex. Whip out the color wheel here. Where does it absorb? green. So we got one down. You see the next one that was green. What a deal. It's just the reverse, right? That one absorbs red. And finally, you see blue. If you look on that, maybe I did this intentionally. You never know. The complex absorbs orange. So the three colors I circled are the ones that these complexes absorb. Let's rank those then in order of energy. Let's start at the bottom. The large energy, large delta O, enforced by the cyanide ligands, will absorb the highest energy. The highest energy has the shortest wavelength. So of these absorbing things, which one has the shortest? It's actually green. So if you look at where it is, green falls between 490 and 560 nanometers. And so what absorbs green? This. The cyano complex. Consequently, what do you see? Red. And so you can see this is kind of counterintuitive, right? We're thinking, okay, this has got a big delta O, so it has a large energy, but you see a short wavelength. Again, this has to do with the fact that it's the complementary color that you see. Okay, so we got that taken care of. The one that absorbs red would have the smallest delta O because orange is higher energy than red is. Because red is longer wavelength. That's going to be this one, this chloro, and so as a result, you see green. And now there's not much left to say. Process of elimination, or by following the same logical argument. This one is orange. You see blue. And so when given a problem like this is how one goes about it. And so it's an electronic transition that occurs. That transition has a specific energy associated and parallel to the size of delta O, which is affected by the ligand set, and therefore, as long as your d electron count is the same, the ligands influence everything. All right. Now, since this can occur for any complexes that have d electrons, what we just said since the beginning of this lecture, well, this colors based on the electronic transition from T2G to EG is relevant if you have d electrons. And for once, I intentionally wrote down the wrong thing. There's two cases where it isn't. If you don't have any d electrons, there can be no T2G to Eg star transition. But if you have D10, what happens is everything's full, right? And so you can put a maximum of 2 electrons in any molecular orbital, no matter how big it is, no matter what its geometry is, no matter anything. Therefore, it's impossible to promote an electron from here, T2G, to here, Eg star, in D10. That is not true for D9. And so those configurations can have these T2G to Eg star transitions that we've been talking about. But there are D0 complexes that are colored, and there are D10 ones that are colored as well. So what's the deal there? And so for this, refer to this part of your handout. Okay, so in on this handout, it was better drawn than what I have here. I'm just showing what's inside here, right? So let's say we have a D0 complex of some sort. Now remember what the deal is, and I'll put the symmetry labels too, just for the heck of it. For any octahedral metal complex, no matter what the d electron configuration is, these orbitals down here are full because they're based on the ligands. And so if you go back to that lecture, when we talked about building this molecular orbital energy diagram up, what you find is that there's 6 pairs of electrons, there's 6 ligands that are Lewis bases donating to the Lewis acid. So 12 electrons total. Those go in these orbitals here. So no matter what you do, it doesn't matter what complex we're talking about, it doesn't matter what the metal is, it doesn't matter what the ligands are, if it's octahedral, this is true, right? Up in here, those are always empty too, no matter how you slice it, no matter what metal it is, no matter what complex it is, right? And so these ones here are full. The ones on the top are empty. We don't know if there's electrons in there or not, but right now what we're saying is There aren't any. But what can happen in these things is that some complexes can absorb enough energy, and so we're talking high energy here, enough energy to result in promotion of some of these electrons into the metal-based orbitals. And so, for this, then, to occur, any of these electrons down here, I picked the bottom one, where the bottom of my arrow is right here. I was promoting it to T2G. You can promote from any place here to any place in here. When that occurs, electrons are promoted from essentially orbitals that are localized on ligands to orbitals that are very much so localized on metal. And what you get when you do this is a ligand to metal charge transfer. Ligand, electrons to the metal, hence ligand to metal charge transfer. That does imply there's some kind of charge distribution change. That's true. We'll get to that after we look at the next case. This is abbreviated LMCT, ligand to metal charge transfer. And yes, that is going to give a colored complex. It's not a transition between our familiar T2G and EG star orbitals, but from these full ones down here to the empty, because it's D0, metal orbitals. What if we're not D0, but D10? So again, this is another situation where this T2G to EG star transition isn't possible because these are full, right? You can't promote an electron from here to here. But what you can do is bump an electron up into the formerly empty orbitals that are antibonding. And when you do that, what we have is metal to ligand charge transfer. So kind of the reverse, if you like. But what you're doing is taking electrons from the full metal-centered d orbital sets that we have here and putting them into antibonding orbitals, which are also ligand-based. So we have metal to ligand charge transfer, MLCT. So what about that? Here's a few things to note. Ligand metal charge transfer. occurs when the ligands are halogens, oxygen donors, or nitrogen donors. It's an intense absorbance. It's a high energy absorbance. And because some electron density is transferred from the ligands to the metal, in effect what happens is the metal is partially reduced. In the reverse, when we have cyanide, or carbonyl, or phosphine, what we have is metal to ligand charge transfer. These same two things apply. Right? There's going to be intense absorbance and high energy. And the metal is partially oxidized because it's losing some of its electron density to transfer to the metals, to the ligands rather. And so if you look on your handout one more time, the CT absorbance is letter A. These weaker absorbances are due to the electronic transitions from T2G to EG. And so, important things to remember about this charge transfer stuff is there's two kinds that it can occur, ligand to metal or metal to ligand. You should know where they transfer, where the electron density comes from and goes to in each case. And also this part, that the metal is either partially oxidized in metal to ligand charge transfer or partially reduced in ligand to metal charge transfer. And so that brings us to the end of this virtual lecture, and we'll have one more transition metal one.